Definitely didn't start already. Whew, okay. So, second derivative. The first derivative would, for this kind of function, f of x equal to x cubed minus 6x squared plus 3x minus 7. We'd follow the first derivative rules, which means we would take a derivative by the standard power rules. 3x squared minus 6x plus 3.
It's 12x.
12x. 12x. How could you?
Unless you do this.
Thank you. Always thank you for correcting me.
Sure he actually got it to say something?
Yeah, sure.
So, a second derivative just implies we take a derivative again. We don't go back to the original function. F double prime would be included as the derivative of this new function. So, let's talk about the relationship between these three functions and how they kind of fit together. So, f of x. This is considered to be the original function. It's your OGF. Okay? This is your original gangster function. OGF. Got it. Thank you. I worked really hard on that joke. Thought about it all weekend. Yes. Sadly. Way too much. So, this function contains values, right? It's like you have heights. You have like coordinates on a plane. This is your standard function. And so you can talk about it the same way you can talk about standard functions. You have intercepts. You have positive values, negative values. You can talk about the slopes of this function and how it's changing. But again, that's still all dealing with the original function itself. Whereas f prime, this is considered to be your slope generating function, your SGF, as opposed to your OGF. Yes. See, it's all coming together. Okay, this is your slope generating function. So what it does is every value that it has, every y component it has, is actually f prime, indicating the slope of the original function. So while the original function, like your y values are just, a value, it could be a height, could be anything, whereas this function, your y values are your slopes. That's how the function is acting, how the function is changing. So what's double prime? Well, first let's remember what a prime does. A single derivative is designed to tell you the change of the previous function. So if you have a function like f, this represents the changing of f, which we call slope. Now, how the function is changing over time, what we call rate of change. So then the derivative of that would be the change of the slope, or the change of the function. So a second derivative indicates to a function how the slopes themselves are changing. So this is the change, or we call it the delta of the slope generating function. So the delta of the slope.
I don't think we need to bring that up.
Oh, but we do.
No, physics got it hammered in my head. I wrote delta.
To put this in perspective from physics, well, this value could be something like a height. This value would be something like velocity. The change in height.
I need the following students to report to the gym, please. Megan Elwood, Carly Cooper, Annalisa Ramirez, Helen Martinez, Taylor Hodgkinson, and Peyton Cooper. Report to the gym, please.
Oh, you still showed up
For
today?
the basketball.
That showed up today and still be quarantined?
Sounds like.
Okay, so in physics, like this might represent height, might represent distance. Another way to say this exact same thing. And so the change in the distance is always represented by velocity. They have a natural relationship there. How do I change distance? Well, I have to have some kind of speed to do that with. So then in physics, f double prime would be the change in the velocity, which we call this acceleration. This provides a connective tissue between the original functions and all their components. If you have, for example, in physics, you'll often see the formula for height or distance. If you take a derivative, it will create for you the velocity function, exactly the way it's supposed to be.
I really wish this class was a prereq.
I know, right? In some colleges, it is. There's a calculus-based physics class, as opposed to what you're probably thinking was a trig and algebra-based trig class or physics class. Yes, there are calculus-based physics classes, which are better.
Yeah, it makes more sense because the entire idea of calculus was set up to do physics, right? Yeah.
So, in the original function,
Why didn't we take physics first?
Oh, no, we should have taken trade basically.
And so you can have an understanding of the concepts before you see them all connected together into calculus. Because imagine this. Imagine trying to learn what velocity was while also learning the calculus equations for it.
Okay.
See what I mean? Like if you understand the idea, then you're just like, oh, so the idea just connects it to something deeper? Oh, that's easy. Good. I got that. Okay, so let's talk about these three functions now. So while this is the original function, it will output individual values, so y values. This function will output slopes, so m's. It'll output what's happening to that function as it's changing. Is it tending upwards? Is it tending downwards? How the function is changing over time. F double prime is the change of the slope itself. We have a terminology for this. It is called the curvature. Curvature. So let me put two functions up here on the board, neither of which are the function in question, but I want to point out a couple things about them. Both of these functions will have a first derivative that is positive. Yet they will look very, very different. So let's remind ourselves, a first derivative that is positive, what's that going to tell me about the original function? If the first derivative is positive. So it tells me the slope is positive, so that's telling me about the original function. It's increasing. Remember, this is how we connect all these pieces together using calculus. Okay, so if I have a positive first derivative, that would indicate that my slope is positive, which indicates the original function is increasing. So it is going up over time. These two functions will both be going up over time, but there'll be a radical difference between them. So over time, this function is tending upwards. So it would have a positive slope. And therefore, its first derivative would in fact be positive. This function is also tending upwards. Yet they're wildly different. They're wildly different because of the curvature of the function. One of these functions is curving upwards, indicating that the change of the slope is changing more positive. The slope is going up over time. So not only is the slope positive, but it is going up. As opposed to this one, on the left-hand side, where the slope is positive, but it's going down over time. How much it's going up is decreasing. The change of the slope is downwards. So again, if we were to draw little tangent lines here, right here, we have a pretty positive slope. We'd say that this has a very positive value. It might be like a 6 or 5 or somewhere in there. Whereas over here, it's still positive. That was awful. Still positive, it's a lot less so. And so we'd say the change of the slope is negative because the slope is tending downwards. Even though it's a positive value still, how it's changing is going down. This is referred to as the second derivatives test. It determines curvature, how the function is going upwards or how the function is going downwards. Now, let's go back to our original three. We'll put all three of these into decimals here in a little bit. We'll see how they kind of fit together. In the original function, we have intercepts. These intercepts occur when the when the y value is equal to 0. So we touch the x-axis. It's the most common one. There are also y-intercepts when the x value is 0. Those are typically less useful in terms of the calculus part of it because they have less deterministic value. We talked about how f prime doesn't have intercepts, it has critical values. These also occur when the y value is 0. So there's a place where we could have a maximum, a place where we could have a minimum, or we could have just a place where it pauses before continuing in whatever direction it was going. These are, again, critical values. Places where the function is clearly attempting to make some kind of change happen. Either it does happen, or it doesn't happen. These are also places where the function is undefined. We have some drastic change. Something massive is happening different. Now, double prime does not have intercepts, doesn't have critical values, has a new and fancy word. It is called points of inflection. These are places where the y value of f double prime is equal to 0. Now, intercepts is places where the value could switch to positive and negative. So it could be above the axis and drop below, it could be below and come above, it could just touch it, but it's doing something interesting there. Critical values are places where the derivative is doing the same thing and therefore tells us something about the original function. You know, it could be a max, it could be a min, it could be just a place where it pauses, it could be an asymptote, because of that not defined portion of it. Points of inflection are places where the curvature can change, where it switches from tending upwards faster or tending downwards faster. It's places where the curvature has a change to it. And it's found in the same way we find critical values, which is found in the same way we find intercepts, by setting an equation equal to 0 and solving. The difference is, which equation are we doing it for? We're asked to find intercepts, we have to do it to the original equation. If we're asked to find it for critical values, we do the second equation, f prime. If we're asked to find points of inflection, that's f double prime. So back here. If I asked you to find the critical values, we'd want to take this middle equation. We want to set it equal to 0. And we want to do the process necessary to solving that function. And keep in mind, from algebra, there's a lot of things we could do. We could have, for example, we could factor, use the fundamental theorem of arithmetic. We could, because it's a quadratic, use the quadratic formula. If it's a special case, we could use things like the perfect squares formula, or difference of squares, or difference of cubes, depending on the function it is. We could be forced to use things like a unit circle if it's a trig function. There's a lot of things we could do. All those things also apply to f double prime, because it follows the same basic rules, just with a different function, f double prime. Let's put these three functions up here on the board onto an actual graph, starting with this first one. So x cubed minus 6x squared plus 3x minus 7. As we look at this function, I want to point out a couple of details here that you can see visually if you have a picture of the graph. As we discussed already, the idea of the derivative is to be able to help us in creating how this function looks, because you can determine things like increasing and decreasing, which greatly affect the picture, despite not having the picture possibly at the beginning of the problem. So x cubed minus 6x squared plus 3x minus 7. What's the odds I'm going to forget that? Pretty high. Let's go to Desmos. Apparently the app does not work anymore.
Yeah.
All right, here we go. Our function was x cubed minus 6x squared.
Yep.
6x squared x plus 3x minus 7. Zoom out a little bit so we can see this function. Okay. So zoom out here pretty far. Okay. So we can see here how we have some things in the original function. You have a single intercept on the x-axis right here. That's what looks to be 5.689. Beautiful. We have a single intercept on the y-axis, which isn't that important to us, right there at -7. From the first derivative could tell us that there are two critical values, one of which becomes a maximum using the first order test, one of which becomes a minimum using the first order test. A maximum over here at 0.268, and it's a local max, because it's only relative to the area around it. And a minimum down there, also with a nasty value. And again, because of all these ways, these tools that we have, we could find all this stuff using specifically the first derivative. But I want to point out something. There's also curvature. Because not only is the function changing over time, it's also doing one more thing. It's changing how it's changing over time. Okay? This is referred to as the curvature. And in this case, there are two ways to talk about it. If it is concave up, or if it is concave down. I'd be like, but why don't they use convex? Boy, if I could tell you, I would tell you. Man, the noise that I gotta be that they never use convex. Nope, it's concave up or concave down.
What's down the way?
It is so annoying. I looked at my, so I got taught by our math department chair at our university. He taught me this particular class, and he was like really upset because like every day he'd be like, okay, are there any questions? And I'd be like, why is it concave up, concave down, and not concave and convex? And he was like, any other questions? I'd be like, answer my question. Never had the answer. Never had an answer. I imagine it's because like there would be an argument about which one's concave, which one's convex. Like is concave up just concave? Or is concave up actually convex?
Pick
Well,
one. Pick one.
Anyways, as we might imagine, the points of inflection are places where you could have changes in the concavity. Or you have places where it could be changing from concave up to concave down. Same with place where it doesn't exist. So looking at this picture, I'm going to zoom in just a little bit here. Looking down here, you can see that from starting at the negative values over here, we have clear concave down because it is tending in a downward change. The slope starts off really positive, still positive, but it's getting less positive. It then hits a value of 0. Then it starts tending downwards. Tends down, tends down, tends down. There becomes a place where the slope has a lowest value, a most negative value. It has to, because it starts changing it. It's still negative, but now it's getting less negative because it's approaching this bottom here. And once it hits that bottom, it then proceeds to go right back upwards. So it is changing over time. And how it's changing, there must be a place where there is a lowest value, what we would call a minimum, but a minimum for f prime, or a maximum for f prime. These are based upon the second derivative. The second derivative determines concavity, and concavity determines by points of inflection, determined when we have y equals 0 or y undefined. So the same way as we can talk about how a function can have a minimum or maximum, we can talk about how the derivative can have a minimum or maximum. And those values are determined by the function above it. We determine the max and min of f using f prime in the first derivative test. We determine the max and min of the derivative using f double prime, second derivative test. Take a look. What else? If f double prime of x is greater than 0, if f double prime of x is less than 0. Greater than 0 implies f of x is concave up. Less than 0 implies f of x, I do it every time, f of x is concave.
That stresses me out.
I know. Once you see it, you can't unsee it. Like the next time you go to Sonic and you go into the drive-thru, look at the picture to the right of the window, because on the word don't, they have not one apostrophe, but 2. Once you see it, you can't drive up there and not see it.
You do?
Yeah, you can't unsee it. You can't unsee. Good choice. Okay. So, this is going to be the part that's going to be real interesting when it comes to your quiz, because the terminology, there's so many ways we can ask similar questions, right? Just like how we've had similar questions being asked with f prime, right? We could ask about the slope. We could ask about the tangent line. We could ask about the normal line, and they're all related to each other. We could ask about a minimum using the first derivative test. We could ask about a maximum using the first derivative test. We could determine local or global. We could determine relative or absolute. With f double prime, we can talk about concavity. But because f double prime also represents the change in slope, we can talk about the maximum slope. That means look at f double prime. We can talk about the minimum slope. That means look at f double prime, because it's the changing values of the function below it. If I want to find the maximum of f, I look at f prime. If I want to find the maximum of f prime, I look at f double prime. Now, going back to our physics. A change in height changes based upon the velocity you're going at. Velocity changes based on the acceleration at question. Now, that's why you'll see that for many functions in physics, they're quadratics when it comes to things like height. The reason being is, on Earth, acceleration is constant, going down at 9.87 meters per second squared. So if you think about it, sorry, 9.81, thank you for correcting me. So if you think about it, that's f double prime. If f double prime is a constant, think about what that tells you about f prime. Remember, its derivative would have to be a constant, so it'd have to be some kind of x value. X times a number. Possibly with a number being added and subtracted to it, because again, those get disappeared after you take a derivative. Which tells you then that if f prime is some kind of linear equation, then f double prime was a constant. So in backwards, constant, linear, quadratic. So it all makes sense. And in fact, we'll talk about next semester how we can find that equation using something called an integral or antiderivative. Before we get there though, let's continue and discuss concavity. Just like with f prime, how you can find critical values using the derivative and setting equal to 0, we can find concavity by taking f double prime and setting it equal to 0. Let's take a look. Here's our function. F double prime, 6x minus 12. So in this case, x equals 2 is what we call a point of inflection. And the place where the concavity is changing. And just like how I can determine the styles of the concavity, I can determine the styles of like increasing and decreasing, I can determine concavity by testing around my points of inflection. So I can again make the same basic table that we did before. This time I'll put my points of inflection here, and I test around it. So maybe at like 1 and 3 or something to determine the concavity of it. This is again really helpful if I don't have the picture of it already, because now I can get an idea of not just is it increasing, but is it increasing more or is it increasing less? Oh, it's decreasing. Well, is it decreasing more or is it decreasing less? Is there a place where it's the most negative in terms of the slope? A place where it's the most positive in terms of the slope? Other applications for this? There is things in engineering referred to as stress equations. Stress equations are places where your machine is likely to break, where your wing is likely to break, where your car is likely to stop working. Well, those can be found using the second derivative. What you do is you take the stress equation and you ask, okay, where is it going to have the most stress? Well, that's a maximum of the stress equation, so you look at f prime. Where you can say, how was the most likely to have the most strain, which is a version of stress. It's the change in the stress. Well, that would be f double prime. So then says, hey, when is it going to experience the most change to the stress? Because that's really important. In terms of an accident, as weird as it sounds, if you were to jump off a building, height may not kill you. You can survive a height from, I think the longest person survived is over 5,000 feet. Just tap into land right. You can survive going really fast. You can survive a fairly high acceleration. Once you get about 9 Gs, you'll black out. What you can't survive is a third derivative called the jerk. While you can survive a very long height, you can survive a relatively high velocity and okay high acceleration. What you will not survive is a jerk. The jerk will cause so much strain in your body you can snap your neck. Your brain could smash into the front of your skull, causing a concussion. Eventually internal bleeding, possibly anemia and death. Ironically, whenever we talk about, I was talking with Garrett this morning, we were talking about how he's worried because he had a nosebleed after one of his tackles on Saturday. He's like, You're probably gonna have to go get tested for a concussion. I was like, he's like, but it felt weird. I didn't get hit that hard. I was like, it doesn't matter, man. It doesn't matter. A person who gets in a 5-mile-an-hour fender bender can end up in a wheelchair the rest of their life if the jerk is high enough. Because again, it's this value that'll kill you. If you think about electricity, voltage will not kill you. Amperage will. It's the same basic concept. Oftentimes, these values become very, very important because of what you're using them for and how they fit into something realistic. We'll stick primarily with doing equations at the start, of course, but eventually we'll look at realistic applications and say, okay, well, what's going to be the maximum area? Well, that's going to be a maximum, so we'll look at the first derivative. Well, when's the area changing the fastest? Well, that's going to be the second derivative, because that's going to be the change of that area. Okay? So, we will look at some more curvature problems tomorrow. We'll actually do some together. On Wednesday, we'll be looking at homework questions. Like I said in the assignment, they are a mixture for this assignment. There's, I believe, 50 problems. There is a mixture of questions from last chapter where it's like, hey, can you still find a tangent line? Can you still find a normal line? Those skills need to stay sharp. Okay? And there'll be questions that are asked about, okay, find increasing, find decreasing, find a maximum, find a minimum, find relative extrema. Those terminologies, they all fit together. Those are the ones that I'm really worried about. Like if you have to skip problems, you can skip the ones that are the normal and the tangent ones. I'd like you to keep trying them, or you can try them over break. Come on. If you want to focus for your quiz is going to focus on curvature. It's going to focus on increasing, decreasing, relative extrema. Okay? But make sure you don't lose those other skills of being able to find a tangent line and being able to find a normal line, that kind of stuff. All right?
Probably, yeah.
Those are this morning.
Okay.
Okay, we got 10 minutes. I'm going to do one problem where you find both types.
Disgusting.
We're going to find relative minimums and maximums using critical values, and we're going to find points of inflection using the second derivative test.
I like this stuff better than last.
I love the application. Learning the stuff initially is kind of boring and annoying and tedious, but once you learn the application, it's like, well, I'm still doing all that stuff, but now it has some meaning to it. Like it has some value to it. It has some F to it.
You want to talk so much for so many ways to go. You don't do math for it.
If your math kills you, I want you to know you are weak and deserved it. All right. Let's take a derivative. Remember, because to do f prime, we just need to take a derivative. So for these functions,
Wait,
no, I would never do that.
Give us a chain instead of quotient.
No, I'm not that mean yet.
Oh, not yet?
Yeah.
I have a question.
No.
So, the 6x minus 12, if you were to graph that, could you find, how would you find the curvature if you just solved that? Like, how
Well, think about it.
How would you know?
Positive values are when it's concave up. So if you were to graph f double prime, the y values where you have a positive value would be when it's concave up. If you want, we'll graph the other two here in a moment. We'll showcase how all these fit together. All right, here's f of x. We could multiply this all out if we wanted to. Nah, won't take too long. And here's the thing, like, some people think this is like a dichotomy. Like, you either have to multiply it all the way out or you have to do it the way it is. There are middle grounds all over the place. Like, you could, if you remember your perfect square formula, just quickly do this piece. And then it's like, you know what, I'm going to do the product rule. Like, you don't have to go all the way in one direction or a different direction. Like, don't assume that's the only options you have. It's a trap, okay? You really need to know that these pieces are fluid. You have as much control over this problem as you want to have over it. Pick the components you want to do, and as long as you're following good algebraic processes and the calculus rules, you will find the solution. So, this would be a version you can use. You can also use the other version, which would be x cubed. Just factor it out.
I just did
Before that.
Just got a factor. Just go back to the original problem.
I'm sorry, that's what I always say.
Nah, you're fine.
Like that, I do believe. I mean, I've been wrong before. I would check it. I think this third one's wrong. In fact, I'm 90% sure that third one's wrong. Let me double check the math here.
Maybe like 25, minus 25.
No, it should be like negative 15x.
Negative 15? Okay.
Yeah, it's x cubed plus 2x squared minus 15x minus
Alright.
36.
Yeah.
Oh,
I personally would have gone right at the product rule and be like, alright, I can do this kind of stuff.
Yeah.
But I'm comfortable with the product rule.
We're having
Alright.
fun.
Okay, so
No, it's different.
F prime.
That's good.
3
Times x plus 3.
You would, Ricky. 2 times x plus 3
Times x minus 4.
No,
times x minus 4
maximum.
Plus.
plus
X plus 3 squared.
x plus 3 squared. I love it, Ricky. Thank you.
Why?
Ricky went back into the chain rule instead of product.
So
So you guys should probably get this other version of it. You guys should get 3x squared plus 4x minus 15. And yes, you were correct. In order to find the critical values, we want to set this equal to 0. Okay, let's talk. What options do I have with both of these functions? Because I have options. Like on this top one, what can I do?
You could just use the fundamental theorem of arithmetic and break it down, so then you have your 2, which can never equal 0. And
Be careful, because that plus sign.
plus.
Now, if we were to factor something out, we could then use the fundamental theorem of arithmetic, which you can do.
X plus 3.
You can factor in x plus 3 from both terms, which would look a little funky. Let me see if I can do it real quick. So you would take out an x plus 3. What we left behind? Well, a 2, an x minus 4, and one of the other x plus 3s. And so we can quickly simplify this inner piece, and then we just do the fundamental theorem of arithmetic. Which would be, let's see, this would become
Yes.
this becomes x plus 3 times, let's see, this becomes 2x minus 8, x plus 3, so that become 3x minus 5.
There we go.
So x equals negative 3 and x equals 5 over 3. These would be our critical values. What if we had done it the other way, where we folded it all the way out, we got down here? What's our options?
Quadratic formula. No.
Factoring, quadratic formula.
How they're not good.
What's wrong with you? Every time I hear quadratic formula, I just like, in my head, like the quadratic formula song plays in my head. And it's not
X
like,
equals negative b plus the math.
Oh,
it's
Square
not
root.
even, no, it's like,
Minus
I
12
just
ac.
understand something.
You've seen it, you just know it.
Quadratic formula.
Okay.
I know.
Any other options here? Factoring works. Quadratic formula works. Any other options?
Probably.
Yeah, probably, right? There's like a bunch of values where you can remember, right? The only thing I could think of was like you complete the square,
Right, but.
which would be annoying and fun. That's pretty much it, though.
Yeah.
Okay, so you have options on how you take the derivative and how you do the derivative for some problems. Let's go back now and discuss what if I wanted to find f double prime.
They're like my first 36 of the period.
First thing to point out, if I want to find f double prime, we have two different derivatives we can work with. We have this derivative, and we have this derivative. One of them is a lot easier than the other.
Top one.
Clearly the top one is so much easier.
It is.
You got a product rule on one side, you got a chain rule on the other side, that's easy. What you'll find is that simplification can help you if you need to take a second derivative. This one, I would argue, because it only uses the power rule, is easier.
Really?
Really. Now, that does not mean you can't find it with the other one, it just means you gotta use more advanced rules. Now, that being said, going back here, Ricky, go ahead and find it with that top one then.
No, Rick is in the month.
Oh, that's
I guess you're gonna have to do it in your head then, Ricky. While everybody else, let's go ahead and take the easy way.
Yeah.
6x plus 4.
Ricky, you done it?
Are you done yet, Ricky?
Are you done yet, Ricky?
Okay, done.
So what would be my point of inflection?
2/3. No, negative 2/3.
Negative thirds. How'd you get that, Michael?
I set it equal to 0.
Yes.
And then I saw shrinks. My eyes. Yeah.
Big brain.
Negative 2/3.
So what's this tell us? -3 could be a max, could be a min, could be just a turning point is what it's called, whenever it doesn't actually do either one. 5/3 could be a max, a min, or turning point. -2/3 is a place where this function is going to have a curvature change, which means the left could be positive curvature and the right negative. So the left could be positive curvature and the right positive curvature, because again, what we found was where it's 0, it's possible it's still curving upwards in both places. And then finally, it could be a place where it's like negative or negative positive, which again, can tell you about how the curvature is going, whether it's concave up or concave down. You wanted to see it? Let's go ahead and go back to that real quick. Here's that other one. Let's put the other formulas we have there. Do you have them written down in your notes, questions? That's okay, I can do it real quick. 3x squared minus 12x plus 3. So this function. So remember, you have to think of them separately but connected. The blue function is supposed to be the slopes of the red function. Does it make sense? Yes, it does. Here's why. To the left of around 0, the slope is a positive value, and if you look at our red function, it is tending upwards. In between 0 and this number, the slope has a negative value. And if you look between that number here on the red graph and that number there on the red graph, the slope is definitely negative in between those two. It is tending downwards. And then to the right of this value, the slope is tending upwards and the function is tending upwards. Whereas in this case, if I go now to 6x minus 12, now the green function, I'm going to hide the blue one for a second. The green function represents the curvature. Notice that to the left of this value, which is our point of inflection, it is concave down. It is opening in a downward direction, meaning over time, these slopes are changing towards the negative, right? They start positive, but they're getting less positive. Then they go negative, and they're getting more negative until eventually they stop going negative right around here and start tending more positive. Again, they don't immediately become positive because they can't. They have to start changing. It's still negative, but it's less negative. Still negative, less negative, less negative, less negative. It's 0, starts becoming positive, then it keeps getting more and more positive, just like how that green line predicts. The green line shows curvature. The blue line shows slope. The red line shows value. That'll be it. I think the clock's off for school is. 1 or 2. All right. Good on Thursday.
I'll check it tomorrow.